looking at the lines, like say for example 3, and then there's 4 here. 4. We always have to divide the space up into imaginary lines. So what we do is normally, if I have a scale like this, I would divide it into like 10 lines. The first line here I call the 3.0 line, and then I go halfway. At the halfway mark, I'd have 3.5, and then the last line here is 4.0. And so if it's right on this line, then 3 it's certain. And then the 0.0 comes from having to make these 10 imaginary lines from 1. So this will be 3.1, 3.2, 3.3, 3.4, and then on 3.6. So you have to do this mentally, 3.7. Okay, this way we have one certain digit. So for example, the certain digit here would be 3 all the way up. Because for certain it's 3 or above or below 4. If it's right on the 4, then that's certain. But we have one certain digit here. Then certain digit is going to be our guesstimate. Our guesstimate, is it right on the line, slightly above the line, in the middle, or almost to the next line? And so our guessing comes from this, dividing it, the space up. But this one's really screwed up with this. This is a graduated cylinder. This is what we use to measure liquids. And there are 2 types of graduated cylinders that are out there. This one is very tricky because take a look at the lines. And when you look at the lines, we're going from 1 to 2. Is this 1.1? Actually, this one's screwed up because it goes in 1.1 and then it goes to 1.2, 4, 6, 8, 10. And so if that one's right on the 3rd line, that's going to be 3.246. That's going to be 3.6. And so this is our normal scale, but this odd grad cylinder, they didn't print enough lines for this. And so the correct answer is it's 3.6. Now, did we have to guess the 0.6? 2, 4, 6, 8, 10. And it's right on this here, so it matches. Did we have to guess the 0.6, or is the 0.6 certain? It's certain. So this one should be 3.6, and if it's right on the line, we call it 3.60. Because the guessing, now this one's a little bit ambiguous because the guessing is going to come here. The next line is 3.8. And so this is 3.6, this is 3.8. And so in one sense, well, what happened to 3.7? So you're thinking, in one sense, we have to guess that, right? But the way this is going to be divided up is what we're doing is we're just guessing, we'd go from, actually, we'd have to make 20 imaginary marks in here, which is probably more. So we put in more. And so it's a bit ambiguous because the 3.7 is missing. Now, if the 3.7 were there, then for sure 3.60. Some might argue that we are also guessing this 10. But in this case, it would be 3.60. Fortunately, I think most of our grad cylinders aren't these 0.2 of a milliliter increment height. Okay, what did you guys guess for this one? I saw like a 3.3 or a 3.4. In this case, 3.5, there's an imaginary line here, and it looks like it's not quite there, so it's like a 0.4 or 0.3 in this case. So then we go over here. Here we don't have to guess, because when I line up the end of this here with the scale, I forgot what I said. right before the 4, right after the 4. It looks like it's right after the 4. And so in this case, we are not guessing the point. It's 3.1, 3.2, 3.3, 3.4. And if it's just right after the 4, that's where we're guessing here. And so if it's 3.40, 3.41, 3.45, 3.4, actually, is that right? 3.5. There. And so here's the guess. So my guess would be this is like a 3.41 or 3.42 if it's right past the line. And the estimated digit is a point, 0.01 or 0.02. Tell me what this top measurement is. How much precision did you do? It looks to be about what? Maybe 54, 53, 55. Somewhere in there. Now, how precise can you get it? Could you say it's 53 plus or minus 0.05? That is, it's between 52.5, 53.4? No. So this one is very uncertain. So, it's just like 50, greater than 50. That's what we'd say. It's greater than a little. This one, though, we could be more precise. Now, this one's marked normal. So this is 45, 46, 47, 48. So this one's between 48 and 49. So here's where the guessing comes on. If it's right on this line, we call it 48.0. If it's right on this line, it's 49.0. But it looks like it's slightly above halfway. So I call this 48.6. 48.6. Or maybe it's right at the halfway. It depends. Depends on where you mark it. If you look at it in the middle of the line or right at the bottom of the line, depends on how you mark it. You can just be consistent. So if it's right in the bottom of the line, you would call it 48 point. This looks like right in the center there, right? So 48.5. Depends on the thickness of the line and how you usually measure these types of things. Okay. How about this next one here? These are from your lab manual, by the way. I call this 35, 36, 37, 38. So it's between 38 and 39. Let's call it 38.1 or 38.2. Just be consistent however you're reading it. This one here. 4.2. Okay, that's fine. That's good. Now, this is a volume, so there's lots of volume measurements here, and then we have some length measurements. So let's rotate this. So we talked about this earlier, where we read between the lines. So for sure, there's no uncertainty. It's 1 inch. Definitely greater than 1 inch. The uncertainty comes in here. And so these are marked in 16ths. So this would be a 8, sorry. Or 16ths, yeah. 16, 2 16, 3 16, 4 16ths, which is a quarter, 5 16ths. So it's between 5 16ths and 6 16ths. And so here's where we guess. It looks like it's, for sure it's 5, so there's no uncertainty there. It's greater than 5. And so the uncertainty comes in this digit here. It's 0.4. So they're just marking it slightly before halfway here. So 5.4 is 8. Just going to give us 1.34. We did something similar to that earlier with this scale. Metric is a little easier because metric is marked in tenths. So that gives us the standard. The only other thing is the temperatures here. Now, I talked about a concave exists, but if we're dealing with mercury, mercury hates glass. So what happens here is mercury doesn't want to touch the glass, and so it forms a concave meniscus like this, or it tries to prevent or minimize the concave this particular case, we measure it from the top of the meniscus. And so here it looks like it matches this line. What is this line? So this is 10, it's 20, so this is going to be 15. And so this is right on the line, so we call it 15.03C. This is 16, 17, so this is between 17 and 18. Looks like it's greater than halfway, so this would be 17.7 maybe. Something like that. This one is between 9 and 10, so it's 9.6. So we can get some more practice. These are in your lab manual, and I think we'll need more practice looking at the results from earlier. Okay, then let's just keep scanning the homework. We're going to look at sig figs. We've been dealing with sig figs in calculations, counting sig figs, and then applying the sig figs to addition and subtraction. So these are problems with that. These are metric to US conversions. Here's temperature, so we just use the equation to calculate the temperature. Normal body temperature is 98.6 degrees Fahrenheit. What is this temperature in Celsius? Here's some, y equals mx plus b type. Just getting the equation of this relationships and proportionality. This is what we did to derive the temperature equation. Some more proportionalities here. Okay. Some density. Let's read this volume. This one we have our standard. This is the type of grad cylinder I think we have. I think we got rid of all the 2/10. And so when you look at your 10 milliliter grad cylinder, which is the little one, you see 8 to 9. So 8.1, 2, 3, 4, 5. So this is normal. The other one was abnormal. So this is going to be between 8.1, 2, 3, between 8.3 and 8.4. So what would you guess there? It's kind of hard to see. But I would say 8.2, 8.3. So the last digit is the estimated digit. Like that. All right, so this is what you did. We measured the mass of the cylinder, and then we measured the volume of the cylinder by water displacement. Okay, here's some general questions, definitions, etc. Then we're going to take a look. And so what you want to do is you want to go through, hopefully make it to the more challenging problems. And so take a look at some of these. All right, one of these, 120, let's do that. A woman has just given birth to a bouncing 6-pound, 7-ounce baby boy. How should she describe the weight of her child to her sister who lives in Sweden in metric units, of course? The metric units we use grams or kilograms here for that. And so let's do this one here. Remember the composite units we did, acre feet? Do you remember that problem? This is the same kind of deal. This is an acre foot type problem. So see if you can figure out how to do this one, keeping that in mind. And so we have a composite unit here, 6 pounds, 7 ounces. And then what we want to do is we want to go to kilograms. So let's figure that out. And so, well, I'll just do it. Let's get that here. And so just like we treated the acre and the foot separately, we're going to treat the pounds and the ounces separately too. So for example, if we want to go from 6 pounds, this is 6 pounds and 7 ounces. What we can do is we can convert the pounds to kilograms. Now the pound to kilogram conversion, we just said, okay, we'll just use the number of sig figs. It's a little bit tricky here as far as what to do with the sig figs because we have 2 different units. So to be on the safe side, maybe what we'll do for the pounds to kilograms is use this one. that is 1 pound is equivalent to 2.2. What should we do? Maybe we'll go to 3 sig figs here. What was it to 3 sig figs? We'll just go to 2.20 kilograms. Usually 3 sig figs for most of our conversions. Actually, we go to 4 sig figs. What was this to 4 sig figs? Do you guys remember? Yeah, 2.204 is correct. But probably this one will be okay. And so that takes care of the pounds. That gives us kilograms. But we also have this 7 ounces deal. And so we got to get rid of the ounces. So what should we do with the ounces? Well, we can use this one, that there's going to be 16 ounces in 1 pound. And so that's going to get rid of the ounces here. In fact, if I look at that, then that converts it to pounds, and this is and. So this is a bit tricky because we have to do it. Maybe what I should have done was do it separately because of how the pounds work out. So this one was not maybe the right path to go on because the units are going to be screwed up here because the pounds cancel here and it gives me a pounds again, and then I have to reconvert it one more time. And so what I'm going to do here, and this is part of the dimensional analysis, is just try this. We'll just try to convert the 6 pounds into kilograms here. And then we'll go with the ounces to pounds to kilograms here. And then combine the two. Just add the 2 up at the end. And so doing 6 pounds to kilograms, that would be 6 times 2.2. Calculator. Actually, if I do 6 times 2.2 shouldn't be too hard. What does it come out to? Oh, I can punch it out too. 13.2. So this is 13.2 pounds. And then 7 ounces to pounds. And so 7 ounces, there's 16 ounces in a pound. And then that gives us 0.4375 pounds. And then there's 2.20 kilograms, which gives us 0.9625 pounds. Now, the way this is going to work is the 6 pounds, that's exact. You know, because the baby weighs more than 6 pounds, exactly. And the 7 ounces, this is going to be our inserted digit. So we have 1 sig fig in our inserted digit here, which means we're only allowed 1 sig fig here. And so technically I should round this, but I'm not allowed multiple roundings in a single problem. So what I'll do is I'll just carry the extra digits and then add these up. And so 13.2 places the uncertainty. Actually, this is exact, so there's no uncertainty here. But the 0.9625, I'm going to subscript these to show the uncertainties here. So this is going to give us 14.1625, and we drop the 6, so it comes out to 14.2 kilograms. Comes out to. All right, 122, we'll look at how many grams of milk are in 12.0 fluid ounce glass. Okay. Number 124, welcome rainfall caused the temperature to drop by 33 degrees. 124 is this. A temperature drop is a delta T, right? Rather than a T. 126, a recipe calls for a 1/4 cup of butter. Calculate its mass in grams if its density is 0.86 grams per cubic centimeter. And 128, in active example 3-29, you calculated what you would have to work 6 weeks to earn enough money, that you would have to work 6 weeks to buy a 1,082 $0.49 television. You would be working 5 shifts of 4 hours each at $9.25 per hour, but alas, when you received your first paycheck, you found that exactly 23% of your earnings had been withheld for Social Security, federal and state income tax, and workers' compensation insurance. Taking these into account, how many weeks will it take to earn $1,082.49? All right, so this is what we're going to do with the end. You're going to work on 128 first, and then we'll work backwards. We'll do 128, 126, 124, and 122, and 120. We'll do those for additional practice with dimensional analysis. So this is a standard problem-solving technique here. So go ahead and get started on 128. How many weeks would you have to work in order to purchase this television set? You earn $9.25 per hour. You work 5 shifts of 4 hours each per week. But you have to deduct 23% of your earnings. That's going to be withheld for Social Security, etc. And so try this, trying to string together some conversion factors and see if we can get it to work out.